is short, so we'll be efficient, but it's not short. It's not too short to spend some time recognizing people who deserve recognition. Oh, before that, so note non-academic competition number 3, right? So Harold, of course, has been torturing you guys for a long time. So your chance to have some revenge. Show us what you think, what you imagine Harold looks like. I was thinking of making, if the design is interesting enough, I was thinking of making a class T-shirt, right? So I survived ESTR1004, and all I got was a silly T-shirt, right? So something like that. So think of some interesting design, and we'll see if we can get the money to make a T-shirt. Okay, free T-shirt. You don't have to pay for it. Okay. So I wanted to take some quick time to recognize people who have done well in the midterms. Now, first of all, let me just say, as I said in the post as well, this is somewhat arbitrary, right? It's based on a somewhat arbitrary number. If you're above this number, I put you on this list. If you're below this number, I didn't put you on this list. Even if you're not on this list, there are many people who are noticeably and obviously doing well in class, but just because I have to recognize some subset, so this is what I'm doing. So if your name is on this list, which is alphabetically arranged, I'd like to invite you to come get your reward, which is a passion fruit for your passion in class, right? So in alphabetical order, Alan, Jin Finglay, all right. So wait, our TA will be taking a photo. So it's an award ceremony, right? So shake hands. Okay, passion. Okay, thank you. Thao Meng. Thao Meng. Okay, good. Good job in the midterm. Okay. All right, passion fruit. Okay. Devon. Oh, not in class. Okay, I get the passion fruit. Justino. All right. Good job with the midterm. I saw you arguing about points yesterday, but still. Hongjin. Good passion. Very good. Yeah. All right. Kitty. I know it takes effort to score well in class, so thank you for all of your effort. Lethian. Oh, there you go. Okay. Thank you. Good job. Here we go. All right. And Martin. Here we go. All right. I really appreciate all the posts also you put on Piazza. Good job. And Mike. Not yet in class. Okay. In particular, I wanted to give Mike an extra award because he's the only one who fully solved question number 10, my favorite question in the midterm. So anyway, we'll give his award later. Patrick. Okay, good job. And Pei. All right. Hey, good job. So in particular, he was the top scorer, so he gets a special team. And Sky. again post quite often on Piazza. I really appreciate it. I'm sure the class does. And Walter. Good job. Good job. And finally, Young. Thank you. All right. Also, one for each of the TAs for all the hard work they've done in grading the midterms, helping me grade the midterms. All right. So, okay, good job to all of you. All right. So let's now begin with the class, where the agenda today, as usual, in the Wednesday class, is to discuss the exercise sheet for this week. So this week's exercise sheet, I think, oh, I haven't switched this on yet. Let me switch this on. Okay, good. So this week's exercise sheet, I think, is a little bit easier than last week, for example, right? Week 5, week 8 are all good. Just a sec, sorry, some audio visual problem. Okay, let me keep this off and just use this mic. TAs, can you go talk to people downstairs? This is creating a lot of static. I don't know what's going on. Yeah. Yeah. Sorry about that. Some AV issues. Yeah, I'll be using this one. All right. So week 8, I think, is a little bit easier. Sorry, week 9 is a bit easier than week 8B, but question number 1 was just basic integration, either directly or computing the potential function. So computing the potential function, we've taught you how to compute the potential function.
No.
It works, but it's creating a lot of noise, like even just by itself.
Hello, hello.
Okay, well, let me try it, but if it keeps making that noise, then maybe we'll have to do something. Okay. Okay, let's try. Thank you. So to compute the potential function, you look at the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. So you integrate with respect to x, right? Integrate with respect to x, and then you have a constant which is a function of y and z. Then you differentiate that and then integrate, and then you're left with a constant which is just a function of z, and then you differentiate and integrate again, and then you find out that whole function except a constant, right? And then the goal is to check whether that potential, so if once you have that potential function, you can compute the value of the integral just by showing, just by taking the value of the potential function at 0.4 minus the value of the potential function at 0.1, right? So that's the method we showed you in the first few videos, and you understand this fairly well. So that's all I'll say about question 1. Question 2, so there are multiple posted solutions over here. So for question 2, basically you've been given constraints. So what is the question itself? The question says, where is it? So hiker, there was a typo here. The hiker wants to come down a 4 kilometer hill given by this equation and ending at this point, at the point 4 comma 0 at sea level. And there are a couple of constraints. We want to make sure that the work done by him is not more than P and so on. So and he can also walk at most at 5 meters per second, right? So now, if viewing the force due to gravity as a constant, we have to compute A, B, and C for the conical spiral that he should take, right? So over here, the solutions that have been posted are mostly okay. Like using those two constraints, the fact that the power is at most a certain amount and the constraint on the speed gives us the values of A, B, and C, and multiple people have been able to solve these. Now over here, the one thing I want to highlight is this is just a question about like a little bit of a concept. It's not a hard concept, but I just wanted to make sure people understand what's going on here. So in this question, the force of gravity, so if we pretend, so part C said find the potential function corresponding to the force of gravity. So here, if we assume that the force due to gravity is minus 100k newtons, sorry, 1000k newtons, that corresponds to something where like if the force is minus 1000 light, and switch on this light. Yeah. Okay, thank you. Minus 1000k newtons, right? So what does that mean? It means that the force field is a constant. It's always pointing in this direction. If this is the z direction, it's always pointing in this direction, and the magnitude is minus 1000 k hat. This is frozen, huh? Oh, okay. So this is what the vector field looks like, right? So given a vector field like this, it's actually a very simple vector field. So this is our f, and now we want to find a potential function corresponding to this, right? So that's quite easy, right? Because this is something like 0i plus 0j minus 1000k, and now you want to find, so that's this capital F, and now you want to find a small f such that the gradient of f is equal to this capital F, and of course, like using the same method that we discussed in question 1. Question 1 is actually harder, but using the same method as in question 1, this small f must be therefore minus 1000 times z times k, right? Because the gradient of this with respect to like the gradient of this scalar function, sorry, the gradient of this scalar function is going to be equal to, so if I set small f, if this is my small f of x, y, z, then the gradient of this function is going to be equal to the capital F that I want, right? And this is similar to what you studied before, like the potential function you studied as the potential function due to gravity is mgh, right? Or minus mgh if you're interested in the potential function. So that's minus 1000 times the force due to gravity times the height. This height is just z, right? Now that's what you've so that is assuming that the force due to gravity is constant. But of course, you know that the force due to gravity is not constant. We know due to Newton's laws that, so as pointed out in part number D, in reality, the force of gravity is not constant, and it's given by this vector function. So the force due to gravity is minus gmm by r square minus g capital M small m by r absolute value r cube times the vector r, right, which is equal to minus GMM by x square plus y square plus z square whole to the power 3 by 2 times the vector xi plus yj plus zk, right? This is the force due to gravity. So, so find a potential function corresponding to this. And of course, you've already studied from physics that the potential function corresponding to this should be gmm by r, which is gmm by square root of x square plus y square plus z square, right? So it should be fairly easy to verify that this is the potential function, sorry, negative sign here. This is the potential function corresponding to, like, whose gradient equals the force due to gravity, right? So this is just to tie together what you've already been studying in physics, you know, potential, the gravitational potential energy and gravitational force, with what you're studying here in this chapter, which is that for conservative forces, the force is a gradient of a potential function, right? So gravity is a conservative force in the sense that when you make a loop in any direction, if there's no other force acting, then the work done is zero, right? So it should be straightforward to verify this part over here. Again, it's not hard, but it is interesting and useful to understand this. Okay. All right. Let's move on to question number 3. Another thing which is actually not that hard. I mean, I know there are many parts, right? So that's what makes it maybe tedious, but hopefully not hard. But there are some interesting and important conceptual points to be discussed over here. So let me discuss that as well. And I apologize for not fully commenting on these solutions before. So I need to award bonus points for the people who posted. I'll do that after class today. I apologize for not doing that before class. Okay, just some deadlines on my end as well. So question number 3. This is basically asking you to see which of the theorems that you have studied regarding line integrals and so on can be used in which context. Okay, so let me first of all remind you what theorems you have studied, right? So theorem number 1 basically says a line integral with continuous components. So a line integral for a vector function with continuous components in a domain is path independent only if the vector function is the gradient of some scalar function, right? So so this theorem holds if these conditions are true. The second theorem says the integral is path independent if and only if its value around every closed curve is 0. And then the third one says so well, a third one, let's look at this one, says if you're interested in this line integral and the function is continuous and has continuous first partial derivatives in a space, then if the differential form is exact, that means it has that means if and only if the function is if there's a differentiable function small f in D such that everywhere in that domain the capital F is a gradient of f and so on. So only if these conditions are hold. So this theorem says if you have an exact differential form, then the curl of f is 0, and this is true. So sorry, and I wanted to also okay, and its components are wait, what did I want to say? Yeah, okay, fine. So this theorem is saying again, as long as these conditions hold in this in this domain, then then the curl is 0, and there is and therefore the partial derivatives of the functions with respect to y and with respect to z and so on, like all of these equalities hold. If so, and this part is usually the subtlest part, so let's focus on this. So if the curl f is 0, if curl f is 0 and the domain is simply connected, then then this function is going to be exact. Then you don't need to actually reverse engineer and find the potential function. Just checking that the curl is 0 and the domain is simply connected means that it is exact, means that there is some function whose gradient, some scalar function such that the gradient of that scalar function is that vector function, okay, without even finding that function. Now, sometimes this simply connected thing can be a little bit confusing. So the point of this whole question is to make you check for continuity, for simple connectedness, and so on, okay. So let's check that. So before we do that, let's look at the question in some more detail. So in this question, first of all, we have some function here which is y square plus x minus z whole square. So first of all, let's figure out where this function is equal to 0. So this function is going to be equal to 0 if so f of x comma y comma z, let's switch to this, f of x comma y comma z is equal to y square plus x minus z whole square. So this is equal to 0 implies y is equal to 0 and x is equal to z, right? So that means that you can imagine it being like, if this is the x-axis, this is the y-axis, this is the z-axis, then y is equal to 0, and in the xz plane you have a line which is going like this, right? This is in the xz plane, it's in the xz plane over here, it's in the xz plane over here, right, like this. So you have a line like this, and this is where f is equal to 0. Okay, how about looking at the next part? So now let's say g is ln of f minus 1. So g is ln, natural logarithm of f minus 1. So I'm just skipping the x, y, z. So when is this going to hold? So for this to be, so when is this going to be well defined? This is going to be well defined as long as f of x comma y comma z is bigger than or equal to 1, right? So let's figure out when is f of x comma y comma z equal to 1. So let's see when that will happen, okay? And of course, you can draw this on maxima, and actually in the solutions that are posted, nobody actually sketched out the region f of x comma z, x, y, z equal to 1, like nobody put a plot over here, but you can do it. You can use the implicit form of maxima and show when show that region. But let me show you what that looks like over here. Here's one way of thinking about it. So so let's look at y square plus x minus z whole square, and let's take a hint from the curve that we mentioned over here. So we mentioned some curve 1 of this form, curve 2 of this form. So if you look at these curves, they look a little bit like circles or maybe ellipses. Here we are giving you a hint, it's an ellipse, right? So why is that? There's some center point, and then there's a cosine and sine form around that center point, right? So if you think about it, if I want to write f of x comma y comma z equal to 1, so I want y square plus x minus z square, y square plus x minus z square equal to 1. One way that I can get a curve on the surface of this is maybe to parameterize this as, let's say, y is equal to, let's say, cosine t, for example, right? And x minus z is also equal to cosine t, right? So if I do this, then as t goes, sorry, my mistake, sine t. So notice then y square plus x minus z whole square will be equal to 1, right? So what is that telling us? It's telling us that a curve on the surface, like when I choose t going from 0 to 2 pi, t going from 0 to 2 pi, I should be getting a curve on the surface of this thing here, right? So what does that curve look like? So so that curve corresponds to indeed curves like this have been drawn by people on maxima. So let's just show you those things instead of making you imagine. So so over here, here the curve drawn has been around a different center. It's been around the center 1, 0, 1, and cosine t like 0.1 cosine t, 0.1 sine t, 0.1 cosine t. So over here, this looks it's hard to tell whether it's a circle or an ellipse, but but in this case we can check and make sure that it's going to be we can check it's going to be an ellipse. So when we get to that part, I'll show you why it looks like an ellipse. So that should tell us so backing up to question number 2, part 2 over here, if x comma y comma z equal to 1 will happen, like if we draw that region, it's going to look like a tube, right? It's going to look like a tube centered around here, so like a tube around here, right? And only outside this region is the function well defined. Like the domain where g is well defined is if f is bigger than 1. So only outside this tube is g well defined, right? Okay, so so now let's go on and look at this function over here. So now capital G is defined as the gradient of small g. Capital G is defined as the gradient of small g. So over what domain is domain D1 is small g well defined? We already said it's well defined outside here. Over what domain capital D2 is the gradient of g well defined? Well, if you think about it, the gradient of g is going to be something like 1 over, actually it's been calculated over here, so let me just show you. The gradient of g is something like this. So it's well defined everywhere except when the denominator is equal to 0, right? So the denominator is equal to 0 if and only if f is equal to 1. So the gradient of g, the gradient of small g, that is capital G, is well defined everywhere except exactly on the cylinder, right? So D2 corresponds to the union of the inside and the outside, right? So D2 is the union of the inside and the outside. D1 is only outside, whereas D2 is inside plus outside but not on the cylinder. Inside plus outside but not on the cylinder. Okay, all right. So now coming back to the question, so is D2 connected, or so is D1 connected or simply connected? So D1 is just outside. So D1, again, let's remind ourselves, so D1 is everywhere outside a tube over here. So it's certainly connected, right? Given a point outside, given another point outside, I can always go around and make a connection. So it's certainly connected, but it is not simply connected. Simply connected would mean that any closed curve can be shrunk to a single point, right? And if you have a closed curve around the tube, you cannot shrink it to a single point, right? So that's why D2 is not simply connected, right? D1 is the inside and the, D1 is not simply connected. D1 is connected but not simply connected. So let's write that down. D1 is connected but not simply connected. Connected, yes. Simply connected, no. Okay. So whereas D2 is neither connected nor simply connected. Why is it not connected? Well, if you're inside, you can't go outside. If you're outside, you can't go inside, right? So it's not even simply connected. So these conditions are important to keep in mind when we look at some of the remaining parts of this question. So so now, first of all, we can check that the curl of G is 0, right? And we said you can use maxima, and indeed that's what someone did over here. So Martin did that over here. He verified, he used maxima dot 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 dot, and in the end 0, right? So that's good. You get 0 at the end. So the curl is indeed equal to 0. So at first sight, it looks like this condition here says if 6 holds. What is 6? 6 is the curl of f is 0, the curl of the function is 0, and D is simply connected, then 4 is exact in D, right? So then you can use those equations. So what is that saying over here? It's saying that since in region D1, you're not simply connected, so that theorem does not hold. In region D2, where you're outside or inside, the thing does not hold, so you still cannot use that theorem, right? So that's why you cannot use that theorem. You cannot use that theorem, theorem number 3, in either of those regions. However, now let's look at this curve C1. So this curve C1, if I think about it, what equation does it satisfy? Like, so if I look at this point 1, 0, 1 plus 0.1 times cosine t times this vector plus 0.1 times sine t times this vector. So first of all, if you just plot using maxima, you will see that this curve is a small curve inside the region. Okay, so if you plot it, it'll turn out to be a small curve within this region. Okay, what's one way to see that algebraically? One way to see that algebraically is, let me just do this here. Yeah, so one way to see that algebraically is, let me write down the equation for this curve. So the equation for this curve is x, y, z are respectively equal to, so x is equal to 1 minus cosine 0.1 cosine t, 1 minus 0.1 cosine t, 1 minus 0.1 cosine t, 0.1 sine t, 0.1 sine t, and 1 minus 0.1 cosine t, 1 minus 0.1 cosine t, right? So if I plot this, so let me just show you. So I just wrote that curve C1 in this format, right? X is this, y is this, z is this. So if I do y square plus x minus z minus x whole square, so y square will give me 0.1 sine square t, and when I do x minus z, this 1 will cancel out, and I'll have 0.1 cosine square t. So that will be 0.1 whole square, right? So this is of course less than 1 square. So that's telling us that this curve is in fact inside the cylinder over here, right? And inside the cylinder, the region is connected and it is simply connected, right? So being within that region, you're both connected and you're simply connected. So since you're connected and simply connected, therefore in this region, we can use the conditions of theorem 3. We have a vector function whose curl is 0, and the region is simply connected. Therefore, the integral of any closed curve in that region is going to be equal to 0, right? We can just directly use that shortcut. So that's why if we look at the question over here, so this is asking, is that vector function dot dr equal to 0 when integrated over that curve? And yes, we can indeed use that vector function. We can use that theorem to compute that integral, right? Now I'm not going to do the remainder of this question in that much detail. I'm not going to do part B, but let me just get you guys started by thinking about curve C2. So curve C2, if you plot it out, is going to be outside this region like this. Okay, it's going to curl around this point, the cylinder like this, and because it's like this, therefore it's not in a simply connected domain, and therefore the conditions of that theorem do not hold, and therefore you cannot use that theorem, right? You have to integrate it by direct integration. Okay, so the whole point of this question is just to get you to think about when can you use the shortcuts that are given to us by theorems 1, 2, and 3, well, in particular 1 and 3, and when do you have to do more work? When do you have to integrate directly? Okay, so that's the points of question, this one. Okay, let's move on to question number, let's see, question number 4 is relatively straightforward. Yeah, I have like 7 minutes, so let's focus on maybe the ones of most interest. So let's focus on question number 5, which I think most of you kind of understand, but I do want to make just a couple of quick points over here. So question number 5 says it's asking you to do a double integral, and in doing this double integral, often the thing that takes the most effort is to write the limits of integration. So to write, in this case, the limits of integration, the inner limits will usually be a function of the outside variable. So in this case, since it's dx, dy, so the limits for the inner integral will in general be functions of y, whereas the outer limits will be constants, right? And if you do the integration in reverse order, well, then the variables change. So you just have to worry about that. And for the center of mass and the moment of inertia, so in this case, Chanyu looked up the, so that's Walter, right? So Chanyu looked up the center of mass formula and the moment of inertia formula. So the center of mass is given by 1 over the volume times the integral of that object, integrating x I hat plus y j hat plus z k hat. Okay, so that's a formula. That's a formula that you can use to compute the center of mass. To compute the moment of inertia, the formula given to us by Walter is that you can integrate that entire volume time by the density times, in this case, the distance from the axis. Okay, so the moment of inertia, if someone gives you an axis, in this case the axis is the z-axis, therefore the distance from the z-axis is x squared plus y squared, right? Given any point x, y, z, the distance from the z-axis is always x squared plus y squared. In the xy plane, it's x squared plus y squared. In the z equal to 1 plane, it's still x squared plus y squared, and so on. Therefore, the formula for the moment of inertia is the distance from the axis of rotation. In this case, that's the z-axis, and therefore the distance is x squared plus y squared times the density, and then integrate that quantity out. That's the moment of inertia. Okay. So that's question number 5 that I wanted to highlight some points, and then question number. So question number 6 is also straightforward. Well, I mean, none of these I think is particularly hard, but okay, we have time. So let's do question number 6 just because it's worthwhile seeing. So question number 6. So in this case, we asked you to integrate some, there's a nice curve down here, someone drew it. We asked you to integrate a certain function within this region. So of course, the reason for giving you that is after you do the change of coordinate system into something like this, then it becomes a much simpler region. Then the region looks like this, and you compute the corresponding Jacobian, and then you integrate, and you get this answer. So I think there were a couple of different answers, some off by different factors, but I think the correct answer happens to be 31 square root 2 by 5. I mean, the number doesn't really matter that much as long as you know what you're doing, right? You can make calculation mistakes. People do all the time. So that's okay. All right. Let's just discuss one other question. So in this case, over here, the question being asked is to figure out what happens when you shoot a bullet through a sphere. So what is the volume of the remaining object? So in this case, what I expected you to do is to use, for example, polar coordinates or Cartesian coordinates and compute the volume. you can either do that by a double integral or by a triple integral, right? A volume is, well, it's in 3 dimensions, so you can use a triple integral, in which case the function you would be integrating would be 1. Or if you use a double integral, then you're computing the volume under a curve, under a surface. And what is that surface? The surface is given by the top of this thing here, right? So when you do that, many of you did that correctly, and you got this answer. What I wanted to highlight was that actually the first solution given used this interesting theorem that basically said that the axis of rotation is given. So if you have a radially symmetric object, if you have an object that is generated by taking a shape and then rotating it, then actually there's a shortcut to doing this calculation. And that shortcut is given by something like by this formula over here, which matches what was gotten by other methods. Actually, next week we'll ask you to prove a generalization of this. It's called Pappus's centroid theorems, or Guldenus's theorem, as pointed out by Vejia down below. So, well, I guess because some of you already used it, so you're getting a sneak preview of one of next week's questions. So we'll be asking you to prove these theorems next week, okay? And I guess the proofs are also given here, so it's not that particularly hard, right? But at least it'll give you some exercise in seeing how to use change of coordinates and proving useful theorems using that setup, okay? Okay, wow, we still have 2 minutes. Okay, let's just very quickly discuss question number 4. Question number 4 asked you to prove the ML inequality. So just like we had something like a ML inequality for the gradient function in, I think it was week 7 or week 6, I forget which week. But similarly, you can have an ML inequality for the integral, for vector integrals. And this is basically saying, if someone asks you to do a line integral along a curve, and the magnitude of that vector function is bounded, then basically at least a useful approximation or a useful bound for that function is to say, just take the maximum value of the magnitude of that vector function times the length of the curve you're integrating over, and this is always going to be an upper bound on that quantity, okay? So just as a rule of thumb, if you want to at least check whether your answer makes sense or not, that's a useful thing to do. And the proof is not that hard. Many of you got that right. So for example, Jinpei's solution is over here, and here Vejia did it by connecting it to the ML inequality we discussed in the vector differential calculus part of class, and so on. So many of you got it right, okay? All right, so again, hopefully this week's material was not quite so hard as last week. Next week will be a little bit harder, but still okay. So that's week 10. Now, I know reading week is coming up, right? So first of all, tomorrow there'll be the project presentations, right? And each of you will be coming, doing the project presentations. Let me just very quickly give you a sneak preview of what will be happening. I've already said it, but let me remind you. So please be on time, put up your posters in advance. We'll have poster boards. Each group can put up their posters. And then the primary goal of the project presentation is actually to learn about other people's projects, okay? So the advantage of this time and the advantage of having 19 different projects is that you can learn from each other and learn many interesting, cool applications of linear algebra, vector calculus from each other, okay? And to incentivize that, remember, in the final exam, there will be a question. In fact, I can even show you what that question will look like. That question will be similar to this question over here. It will be similar to this question from this final exam. Oh, not this one, right? Not this final exam, the other final exam, right? The final exam that looks like this one. So it will be basically an essay type question asking you to describe briefly some of the other projects, okay? So describe the goals, describe the methods, what mathematical ideas were used, and so on, okay? So that is just to incentivize you to learn from each other's projects, okay? So please come early, spend time, we'll give you food, there'll be food, and there'll be a chance for 3 teams to win audience awards. Okay, like if you impress your classmates, we'll have some voting at the end. Okay, and if you impress your classmates like your projects, we'll give you some nice little prizes. Okay, like non-academic, it won't be points or anything. We'll just give you maybe nice fruits, maybe whatever else is around tomorrow. Okay, but I'm looking forward to the project presentations. I hope you are too. So looking forward to seeing you in class tomorrow. So remember, the project presentations will be on the 6th floor of the other building. Okay, so Ho Sin Hang building. See you in class tomorrow. Remember to hand in your slips. Okay. All right, class is over. See you tomorrow.